A warm welcome from a rainy weekend in Uvascula. We want to talk about Muckenhoupt weights. These will provide us a large class of Sobolev functions to test our abstract metric measure theory of Sobolev spaces against. The space is built upon the familiar Euclidean space with the standard Euclidean distance. So as a metric space, it's none other than the familiar Rn. But for its measure, we want to modify it a little bit. One way to construct new measures out of old ones is to have weights. With that, what I mean is you have a measurable function on Rn that is non-negative and locally integrable. Then you define measure of sets, say Borel sets initially, to be integral of omega x over that set. This is absolutely continuous, for example, with respect to Lebesgue measure. So, by the way, dx will always mean Lebesgue measure. For example, if Lebesgue measure of E is 0, then immediately we see that mu of E is 0. So it's absolutely continuous with respect to Lebesgue measure. And in general, this gives us rather well-behaved measure. However, it can also be uninteresting, for example, if Wx is 0 almost everywhere or infinity almost everywhere. Well, infinity can't be the case because of local integrability. Anyway, the AP class for the p parameter between 1 and infinity is a nice, let's say, class of such weights. So weights with certain conditions that result in many things. And to illustrate the idea, let me just deal with the case of p equal 2. So A2 will be the class of those weights that are positive and finite almost everywhere. And the more important condition is that the integral average of omega against Lebesgue measure over a ball times the integral average of 1 over omega over same ball remains bounded independent of the ball. So if you take supremum of this quantity over all balls, all centers, all radii in Rn, this remains bounded. And this supremum actually sometimes is given a name, which is the constant of that weight. So this is A2. So this condition basically says that W cannot be concentrated around 1 point. So it cannot be like a delta Dirac type of weight. And so it's kind of a balancing between how large and how small W can be. It forces it to distribute nicely. For example, if omega is just a constant value, it satisfies this obviously. But then the measure we construct is just a multiple of the Lebesgue measure. So there are examples. The interesting examples is when W actually visits 0 and infinity. Often weights of this type are interesting to us for positive. Thank you for the new subscription, by the way. So for certain alpha, which could be also negative, and the right parameter alpha will put W in the right AP. So these are kind of the typical AP weights. Okay, so with this then you end up with the metric measure space Rn, Euclidean distance, and this omega. So what is a general AP1 and why are they important? Instead of repeating and writing down from scratch, I decided to show you from some resources. So this paper, very readable paper by Tero Kilpeläinen, who is currently the head of our department here in Jyväskylä, has a very, let's say, graduate student-friendly introduction. And there, the Muckenhoupt weights are defined and some basic properties outlined. So for general P, you have this condition, as you can verify. Yes, so for P equal 2, it is exactly the condition that I had. All of a sudden, I thought there's another negative power. Fortunately, there isn't. So again, notice that P is bigger than 1. So 1 over 1 minus P is negative, which means the second integral in 1 is actually Wx in the denominator. So basically, similar idea. In this particular paper, P is assumed to be strictly bigger than 1. For P equal to 1, of course, this definition, as you can see, doesn't work. And there is a different definition using essential supremums. If you're interested in all cases, I recommend the Wikipedia page, which is quite nice on this one. So for the case of P equal 1, let me see. Unfortunately, I can't find the definition with essential supremum. Maybe you saw it and I didn't. But anyway, so where do significance of AP weights come from? Originally, and the reason they are named after Muckenhoupt is this theorem 1-2. Remember the maximal function from previous work we have done here, and take note that this maximal function is again using the Lebesgue measure. Okay, it's very important. So the original maximal function, not with the new measure. What Muckenhoupt proved is that the maximal function, remember maximal function was LP to LP bounded when P was strictly bigger than 1. But what is interesting is that if your weight is in AP, then the maximal function is LP to LP bounded in the sense of LP against this measure. So let me go back to my notes and write down a few things. So LP, we can say over Rn with respect to this weight. Or I actually like to write just LP with respect to this new measure, is the class of, by the way, if your weight is AP, then Ln and mu become mutually absolutely continuous, which is again easy from the fact that we have positivity almost everywhere. And from this, it follows that the measurable functions, sets and functions, are the same. So when you say a function is measurable, it is without ambiguity. Is it measurable in the sense of Lebesgue measure or this new mu measure? So it becomes the same. But anyway, so LP of omega becomes just measurable functions with f to power p integral against this d mu finite. And also it's a nice exercise for you to verify that integrating a function against d mu on any set, well, we can, without loss of generality, do this by multiplying by characteristic function, is nothing other than just f of x, and d mu is, so this one. So we can integrate against Lebesgue measure by paying this density. So this is an exercise actually to be proved, but not also difficult if you are familiar with, say, Radon-Nikodin differentiation theorem. But anyway, so this is LP of Rn omega. So previously we have seen that the maximal function takes LP of Rn to LP of Rn is bounded. So this is in Lebesgue measure. But now we want to, so what the question that Muckenhoupt asked was, when is this maximal function, as it is defined, no modification there, when is this bounded with respect to the new measure? And the answer is that this is bounded if and only if omega is in AP. So that is the theorem of Muckenhoupt giving the name to these weights. So that's one natural way where Muckenhoupt weights appear. And we have seen how important the boundedness of maximal function is. We used it to show why Sobolev functions in the classical sense coincide with high-wash Sobolev classes, because you needed the boundedness of the maximal function of the gradient. So now that we have this again for the new measure, one can show that high-wash Sobolev class for this metric measure space, Rn, standard distance, and mu, also coincide with defining the Sobolev functions on this space as the closure of C infinity functions. I'll come back to that remark. I haven't talked about Sobolev functions on this weighted Rn yet, but so that was originally done in paper of High-Wash. After he introduced the High-Wash Sobolev class, he gave a proof of Poincare inequality for this weighted Sobolev functions using his abstract Poincare inequality there. Okay, so let's read a statement of 1-2. Suppose that omega is a non-negative locally integrable function in Rn. If you are an AP weight, then there is a constant which depends only on the weight and this parameter p, such that the maximal function is bounded LP to LP. LP norm of the maximal function is bounded by that constant times LP norm of the function you started with. For all, And conversely, if this boundedness holds for all functions with some C independent of f, then the weight belongs to AP. So this is an if and only if condition, which again makes them natural objects. Okay, so now let me go back and clarify a few things that I said on the fly. So one way of defining weighted Sobolev spaces on Rn distance and weighted measure is similar to what we do also with the classical Sobolev functions, by defining them as the closure in the appropriate norm of C infinity functions. So in the classical case, you take W just to be 1, so that means there is no weight, it's just the Lebesgue measure. And the norm, the definition you see in the formula is just Sobolev norm. So if you take C infinity functions and take their completion in this norm, you end up with the Sobolev space. Another approach in the Sobolev class, in the classical Sobolev space, is you just take integration by parts formula and you look at weak derivatives or distributional gradients, let's say. And to be in W1P means that you have, first of all, a weak gradient, and number two, both your function and the derivatives, the partial derivatives, weak partial derivatives, whatever you call them, also belong to LP. And you can do exactly same thing. So, but the definition of the integration by parts here will not use Wx. So you will say F defined on Rn has weak partial derivative this if integrating f against partial of any smooth function equals integrating this weak derivative. This totality of this is just one function, so it's not, the notation is, there's abuse of notation. We don't know if this is even a function, it's just a distribution, and then phi. And this is now against dx still, there's no weight involved here. So if such a thing exists, if such object exists, we say that it's the weak derivative of f. So we say f is in W1P if f belongs to LP and partials of f belong to LP. Well, you do this for all coordinates. In the weighted case, you say that f belongs in W1P with respect to this weight if, first of all, this star again holds, and not analogous star, it's exactly the same star. You don't include this W in here. So it has partial derivatives in the usual sense, but then comes the integrability part. So what changes is the integrability part. So f belongs to LP, not of Rn, but this new measure, and partials belong to LP of mu. So certain functions that are in usual W1P may not be in this class. For example, what is integrable? If this is integrable, that does not by any mean force this one to be integrable, because this can blow up too much in places where f is also large and ruin the boundedness. Okay, so that's also the second approach to defining Sobolev functions. And the nice result, again, very similar to classical cases, that both these approaches result in the same space. So whether you begin with C infinity functions and take completion with respect to this norm, or you talk about distributional derivatives and say that your space are those where the distributional derivatives are in the LP omega. These result in the same class of functions. Okay, so when I talked about Hajwas-Sobolev class coinciding with this, so I'm adding a third equality here, that and both of these equals the Hajwas-Sobolev class for the case of P strictly bigger than 1. And the proof is basically because the maximal function is bounded, and the same approach works. So you use the boundedness of the maximal function to produce a Hajwas gradient. So I want to finish this by pointing out some more properties, the most famous properties of Muckenhoupt weights. So the example of powers of absolute value of x, the blow up near the origin are given here. So this power gamma is in AP if gamma is between these parameters. So that gives you examples of non-trivial weights. Okay, so the properties, maybe it's easier to list them together than turning pages. So some properties of AP weights. Number one is that A1, which we haven't really defined, is inside every AP, and every AP is inside AQ if Q is strictly bigger than P. And these are inside A infinity, which by definition is union of all AP. So if you are in A infinity if and only if you are in one of these APs. The proof of this is again a very, very easy exercise and a cool one. So using Hölder's inequality, I really encourage you to try this. The much more difficult theorem is that if P is strictly bigger than 1, then, let's also exclude infinity, then there exists some epsilon positive, which depends only on P, such that a P minus epsilon is includes a P. So this direction is already included in the first bullet point. If you increase this P, you get larger class. But the interesting part is that you can also go backward. This is not Hölder inequality. Hölder inequality gives the opposite direction. So these are sometimes called reverse Hölder inequalities. The Wikipedia page again has nice discussion of these. So this is a very important fact about Muckenhoupt weights, and this has also been proven very differently as a corollary to the famous result of Keith and Zhang from open-endedness of Poincaré inequality. So this 2006, I guess. So they proved that if a space under mild conditions satisfies a P Poincaré inequality, then it satisfies a P minus epsilon Poincaré inequality. And as a consequence of that important result, in particular, you get this. Back to a bit easier fact is that this mu is doubling. So one of the properties of metric measure spaces that we said is important is the doubling condition. So this means that the measure, so there is a constant, universal, independent of the ball, so that the measure of ball of twice the radius is bounded by this constant C, measure of the ball itself. And this is again happy news because so many things, so many results about metric measure spaces use doubling of the measure. And then, let's say without specifying, so certain QP Poincaré inequalities, which are also called Sobolev Poincaré inequalities hold for W1P of R and the weighted Sobolev functions. These are sometimes called Muckenhoupt weighted or AP weighted Sobolev functions. Okay, so let me check one last time if there is something that I wanted to mention. Sometimes I record videos and then I realized I forgot to mention some cool facts. So we talked about this and all of this. Okay, maybe this one here. If W is an AP, just because of the symmetric nature of the definition with 1 over W, so this is basically saying that 1 over W is also in another AQ where you can just compute what Q is. Maybe that can be the last exercise here. That if W is in AP, what what AQ is this W to the power 1 over 1 minus Pn. And that is just by chasing the definition. So anyway, we have a very concrete, hands-on example of a metric measure space that later we can refer back to when we have new theories of Sobolev spaces and when we want to test theorems like Poincare inequalities and stuff. Already we saw that the self-improving of Poincare inequality, that you can, P Poincare also means P minus epsilon Poincare, was related to open-endedness of the AP weight, that if you're an AP, then you are in AP minus epsilon. And this has to be the case if we have two-sided implications. Thank you for the time and have a great day.